really excited to introduce our next speaker. John Whittaker comes to us from University of Manchester, the UK. I'm in particular excited to introduce him because we share something common. We like to make and scale up materials for others to use it at a industrial scale. He has more than 30 years of experience as an engineer, and today he will be telling us about the scale-up challenges of 2D materials, prototypes, and beyond. John, the floor is yours.
Thank you, Omar. This is my first trip to this conference, so I thank you very much to Tony and Natalie for making me feel welcome. But it's my talk is not going to be as fundamental as Andre's. It's going to be more about the journey of 2D materials, certainly over the last 10 years at Manchester. And we're going to be demonstrating the journey that 2D materials, graphene and 2D materials into applications has gone through. The talks this morning from Omar and Mohammed were a really good insight into industry-led challenges. So at the Geek at Manchester, so we're going to be covering some of the data in the applications, but I'm just going to take a few moments to explain the second institute at Manchester. So Andre comes from the National Graphene Institute, which is our research-intensive institute at Manchester, but we have a facility at Manchester, about 8,000 square meters, about 40 applied scientists, and the core of this facility is about industry-led challenges. We've been open or operational now with COVID aside for about 6 years, but its fundamental concept was to how do we take graphene as the first 2D material isolated into applications, but then how do we take the families of 2D materials which are on the same pipeline, the same R&D pathway as we call it. So we wanted to create an ecosystem at Manchester that allowed us to do that through collaboration with industrial partners, other universities throughout the world, to try and transfer that knowledge and understanding to those partners. So this particular building has been open since 2018, operational for about the last 6 years, but it's wholly industry-led. All the activities 100% industry funded. So we're not driven by core R&D programs. We don't do a technology push onto the market. It is fairly unique in the sense that industry comes to the Geek in many aspects. So those could be the multinationals, those could be medium enterprises, or those could be startups, and they all go through individual challenges. I was looking at some data previously just before I came, just to give you an idea of the number of projects, because everything's derived on projects through the Geek, and we're currently up to about 500 projects with about 400 different companies. So it's roughly around 100 projects a year, but every project is very unique. We've highlighted some of the industry challenges today. So if there's a defined, like if you take Omar's talk before, there was a very defined end goal, and we've all highlighted today all those challenges that you have to go through, whether that's price point, the time to market, the adoption, what we call adoption readiness. So I'm just going to talk you through some of those kind of key indicators that either startups or the multinationals face, and then I'm going to be going through some applications data just to show you how we go from the theoretical to the practical around graphene 2D materials. So this is our standard technology readiness, which in university worlds, we're quite happy about the concept of TRL levels 1 to 3. But as you go up the TRL readiness scale, you then start to get into where industry sits. And the challenges in industry, the challenges of development, as we've highlighted today, is a different ball game. We're often the material supply chain. So if we start talking about graphene, for example, one of the challenges 10 years ago was we had the superlatives. We knew how we wanted to get graphene into the system. But the price point of graphene was astronomically high and unadoptable just from a cost perspective. This is not just a knowledge and understanding about how to get it into the various systems. I'm going to give some examples of that. But the material supply chain for graphene was not mature enough. So Doesn't matter whether we want to or we can demonstrate the readiness of these materials and the performance of these materials. If the supply chain is not there, it is very, very difficult to adopt. Graphene has moved on. You know, there are graphene suppliers out there that are making graphene per the ton. These are good quality graphenes. These are very highly optimized graphenes, and we can actually demonstrate proper data. However, there are a lot of carbon black suppliers that are actually now calling these graphenes, and they don't really exhibit the graphenes as defined by the ISO standards. So there was a lot of unscrupulous companies out there that were just using graphene by the name. So these are some of the challenges that we had in the very early days. Things have moved on in the last 5 years. We've actually moved on to now where through the GEEK and what we call the Valley of Death, it's not just the GEEK, the partners, whether they're universities or companies, we've enabled to start bridging those challenges. And some of those challenges will be starting to address the system readiness levels that we have to achieve, and that leads to the manufacturing readiness levels. But as you then go, so companies start to need to see how do we address those, for example, regulatory standards. How do we get graphene, how do we get 2D materials into a system where we can demonstrate we can actually meet automotive grade polymers, for example? How do we get them into construction materials where we can actually meet those standards? So as we go along and demonstrate that the volumes are there, so if we do want to start adopting some of those materials, they are available with data sheets, they are available in terms of tonnage, they are available in terms of geopolitical positions as well. So all these start to come in, but this curve actually gives you the impression everything's legal, but, everything's linear, but unfortunately it isn't. When you go from one stage to the other, so if we come back to say TRL level 3, we focus on, in the GEEK, going from TRL level 3 to about 6 or 7. So this is the prototype and just above. Getting it to that prototype stage actually starts to attract the investors. We're starting to de-risk the process as we go. So we're going to cover some of those technologies and some of the individual challenges that those technologies bring. But it's trying to bring the SMEs or the multinationals on the journey and de-risking at the stages. So the GEEK, Graphene Engineering Innovation Centre, really focuses on those challenges. That when we do get to the industrial collaborators and then they start going to scale, the actual MRL, which is the manufacturing readiness level, is starting to increase, and we can start to get these products to market. But it's not linear in time either. You can get stuck quite easily at TRL level 4 and 5. Even going from the conceptual data, demonstratable data, which might sit around TRL level 3, it could take sometimes 1 year, 2 years, 3 years before you can progress on to the next stage. How do we do this at the GEEK? So we have multiple platforms. So we are the materials developer, but we don't profess to being the world expert in construction, for example, or cementitious materials. We rely on the partnerships we have with the supply chain to bring that knowledge and understanding. So some of the excellent work we've heard about this morning and yesterday, you know, we form a part of the catalytic actions that need to occur to actually progress those technologies. And you've heard some examples today, but we do have core labs, application labs, and the application specialists are largely from industry. So they've worked in R&D in industry facilities, and they have got expertise in deposition technologies, in composite technologies. We've got membranes and coatings and constructions, and our energy systems. Our leads in these areas have actually got experience of scaling to production. And when we talk about manufacturing leads as well, thinking about the ISO production processes that you have to consider, because this is about de-risking, and then there's some supporting activities that come in. We're going to delve into the engineering support a little bit in a moment, but the research technicians and the application specialists are really those industrial specialists for helping to help technology on the journey. We also bring in health and safety, and safe handling of materials, because as you start going up the manufacturing readiness level and the system readiness level, you need to also evolve and develop those techniques so these materials can be handled safely and at volume. Sustainability is a huge lead. So you may have seen these before when we talk about the laboratory scale. We're producing materials on the grammage, sometimes up to tens of grams, hundreds of grams, and then it just becomes a batch process to get up to the 1 litre, the 10 litre. But once you start going beyond these kind of volumes, you really need to start bringing in continuous flow processes, whether that's done by batch or continuous flow. So the diagram on the end just represents type of the automated processes. Now this could be a roll-to-roll system, this could be kind of a continuous flow reactor, which is shown here. But as we go around developing the chemistries, the 2D materials, getting them into the systems, developing the pilot hall. So we do have a pilot hall kind of mentality that we have within the geek, but it is about going from those 1 kilograms to within the geek, we're working around the tonnage scale. So different reactors, different chambers, different drying processes. It's this scalability, but we're starting to get to the design criteria. Now, when you're starting bringing on then design architects, so then these are process control engineers. The control engineers start to bring in what they call the SIL or the SIL processing. So this is safety integration level. This is done at the quite small scale. So typically, if your reactor like this might hold 50 litres, 100 litres, maybe going up to the quarter of the tonne. But you're bringing in the safety regulations as you go. So you've de-risked. When you then go to the pilot hall, you can then take this design and go to the larger scale. And for the venture capitalist people who are starting on this journey with you, they start to see where the price points are, because CapEx is the big killer for sometimes the adoption of technologies. And also, are the materials sustainable? Are the materials that... So you've got to answer these risks as you go on the technology pathway. So we talk about a make or break cycle. So largely, if your R&D is funded by an industrial leading challenge, you've got certain KPIs that you're meeting for a certain technology. Sometimes if startups leave universities, so we have a lot of PhD students who've got very successful startups at the university, but is their technology scalable? Not all technology does go through that scale process or satisfies all the criteria. Sometimes it's the first iteration may fail, and they may have to look at a second system or a remodified system. So what we try to do, we call it this prototype make or break. If we can break early and fail fast and fail cheaply, it is actually the best way to do it. We may go around this cycle several times before we actually get to a successful prototype. But what you're doing all the time is you're de-risking investment kind of going forward. So at the Geek at the moment, on average for the projects we run through, we're working on a 10% failure rate, which sounds not... What that means is the pre-selection we've done, the triaging we've done with the startups, with the supply chain, 90% goes through the solution into a validation and then going into upscale activity. So we do a lot of de-risking with the R&D partners. So we're not dictating, often we're doing a typical process may be, a startup may come with a good idea and we'll say, okay, let's take your idea, let's replicate it. Can we commercially, can we independently verify what you're doing? Just to say if you're going into industry, so what you create in the lab, can a third party produce using your recipes, using your R&D? And then as we go through with the application specialist, we actually develop this prototype and make circuit. And it's quite an important aspect of what they call the make and break. And it works very well. So that doesn't mean to say every solution then that goes through to the next stage of scale up is actually going to make it through to commercialization. This is just the prototype make and break. The next stage then is taking that prototype then potentially into a system and into an environmental demonstrator. So if you take a battery, for example, that's getting it into getting your technology, which might be an anode development. We're going to give an example of this in a moment. But then how do we get that into a standard pack that can go through the volumetric cycling, then get it into a pack, then that can potentially go into a vehicle for further environmental testing. So there's challenges at every time, but we're going to address some of those now. So one of the areas where graphene 2D materials is being used quite a lot is in the construction industry. So this could be in carbon reinforced systems for pultrusion, for structural composites, but we're going to focus a little bit on low carbon concretes. So there's plenty of demonstratable data in papers that suggest that you can get significant uplifts by the implementation of graphene into cement, and that obviously transfers into concrete. And when you're given concrete in the world accounts for around 6 to 8% of all the CO2 generated in the world, there are key significant drivers around sustainability, net zeros for adopting these kind of low carbon systems. So these various low carbon systems, we're going to focus just on one of them, but it's just to give you an idea of some of the strategies that we have to go through just to consider the adoption of one of these. But you can clearly see the worldwide drivers for net zero, especially when cement is got such a high carbon content. So some of the trials we've done have allowed us to increase construction materials by, so this data set that we've had here, we've worked with about 5 or 6 low carbon manufacturers, and they're using graphenes either as a dry dispersant or in a liquid dispersant as an admixture. And there's been lots of publicized data, but the adoption by the supply chain has been quite slow because largely the results have not been replicated in the field. So the consistent results in the laboratories where they've been getting 30% uplifts, and certainly on the 3-day and 7-day tests, the papers and the tests in the laboratories have had up to 40% improvements in compression strength and flexural strength. And this is quite significant because you can take significant amounts of cement out of a system and lower your carbon footprint per tonnage of concrete. However, those trials in the fields have undergone quite significant challenges. If we take the cementitious system itself without graphene in, it's quite a complex system in itself. And trying to get consistency just on normal cement, there's about a 10% variance. So if you go to a good supply chain partner, and one of our supply chain partners, which we've done pours in the UAE here, in Abu Dhabi, but also back in the UK, and we've done them in Europe, Cemex, for example, they can demonstrate just by general mixing, they can get a 10% uplift in a concrete mix itself. So if you take a standard C30 mix, which is a 30 MPa mix, they can improve the strength of that concrete just by the formulation of the concrete itself without putting any graphene in. So this data here is actually standardizing that data. The control is actually, all these trials have been done with the CEMEX standard and other partners as well. So if you take the control and then with the graphene dispersed in liquid form, which is in these ones, we've had consistently about a 20% uplift at the 3-day, 7-day and 28-day. We can get higher, but this is actually taking a standard baseline across, we've done about 16,000 tons of concrete in different conditions with different aggregates, with different surfactants, but this is a good baseline measure now. So the industry data, the large-scale port and the industrial trials we're doing, we're actually using this data now as our starting point. So with confidence, and we're working with the supply chain and the regulators, we can actually start to demonstrate. Now, can we actually demonstrate a 30% uplift and a 40% uplift? Yes, we can. Can we do that consistently? We can certainly do that around 20%. There is actually, you can get high, you can actually optimize it to have a higher say 7-day setting time, we can get 30% within the 7 days. Now, so if you start to look at the value, graphene is about, good quality graphene is about £1,000 per kilo, but the loadings per ton is about 0.05%. So very, very low loadings. So the cost per ton of graphene is quite low. But if you take the 7-day trial on a precast, you can actually start to use that precast and transport it. Rather than waiting 28 days to transport it, you can actually transport it in the 7 days and start to use it. So the value graphene brings is not just in the performance of the material, but in the usability of the material as well. And we can also control things like, well, I'll show you about water, crap propagation and early days hydration. I'll give you some data. But the key thing is the early up strength. Now, if you actually look at the dispersion of dry powder systems, this consistency is much more difficult to achieve because you're dealing with such low volumes in a large volume dry mix, and it's fairly difficult to get that consistency. You're then talking about it becoming quite a disruptive process at the casting stage. So when you actually start to build your concrete, mix your concrete, you don't want to be investing in new plants. You want it to be adopted into the current plant. So this is the supply chain, and this is why it's important to work with the supply chain, because they actually will set the standards about low-cost adoption of the technologies. Some of the flexural strength has also been showing similar uplifts. So this is 20% uplifts in 3-day and 7-day, and 28-day over the same design mix. We've got, how do we do this, and how do we bring confidence into the system? So within the Geek facility, we have a construction facility, and we're using the same ISO and ASTM standard testing techniques that industry would use. Industry then work on the supply chain, work on the mixtures with us, with the admixtures and the supply chain, and the data we generate within the Geek is actually transferable to their own laboratories in CEMEX testing facilities, for example. And that replication of the data showing reproducibility brings confidence. But typically we're talking about these 20% plus improvements. So how does the mechanism work? There's lots of modeling, but largely if you look at the interface zones, which is really between the aggregates and the cement, we're actually starting to show that if you can actually map the dispersion of the graphene, whether it's done by dry or done by liquid, appropriately, we can actually start to see. So we're working with the University of Manchester's electron microscopy facilities, and we're actually doing a lot of cross-sectional sampling to understand the mechanism more. But there's still quite a lot of quantification that's got to be done. Certainly about how we can improve hydration, how we can improve mobility during the mixing processes. I say cementitious systems, it's an intensely physical chemical process, and we're trying to use the graphenes and its immense surface area to actually provide additional nucleations in this point. So it's quite a difficult process to try and quantify once you've actually got it cast. But the mixture of the graphenes and we're managing to disperse it into the fluids and using the liquid-based systems, we're getting very consistent results. We don't get those consistent results with the dry systems at the moment. There are other benefits. These are not fully quantified at this moment in time, but with all concrete systems, you do get shrinkage. It's just part of the natural design of the system. You can't get away from it. But certainly what we have shown is the microstructure does change, and we do get reduced shrinkage. And then when we actually start in doing water ingress sampling, we can actually improve concrete. So we can actually start to tune the concretes for different applications. It's not been wholly quantified that much at this moment in time. But again, using the high selectivity of the materials, we can get significant improvements in here as well. So that's construction materials. That was just on cementitious stuff, but we've actually been working in pultrusion systems like carbon fibre reinforced systems, lightweighting of bridges, for example. We've worked with the supply chain to actually deliver for humanitarian lightweight bridges, for example, and we've been taking material out in things like pultrusion systems, blown fibre systems, so thermosets and thermoplastics, but very similar. It's how do we start to get graphene and 2D materials into automotive grade plastics or aerospace-based plastics, thermoset CFRPs. It's different technologies, clearly, but we've got a lot of demonstratable data here at the moment, and these are some kind of figures that we're getting quite reproducibly at the Graphene Engineering Innovation Centre in all types of systems. So we have laboratories which have standard industry processes, such as injection molding or extrusion systems, where the partners will actually come and understand the formulations, how to get graphene into their thermoplastics, and then how to get it back to their plant, and how to replicate the data we've done. So these techniques such as master batching, for example. So if you derive a thermoplastic, you might want that in a concentrated form, and then you might need to then run those trials back at the thermoplastics plant. How do you draw it down to the usable weight, and then how do you go through that thermoplastic process on their injection molding systems? How we do that, we do have injection molders and extruders at the Geek, where we actually work on that formulation development with the supply chain, so they understand the dispersions and the parameters around it as well. So if we take T300 and T700 systems, we're typically on weight percents again of less than 1%, typically 0.05 to 0.0%. So the price point in these lightweighting systems is quite significant, because when you add the strength improvements that you can get on these polymer systems, you can actually then start to lightweight some of those. I've got some examples next. Syntactic foams is another area, which is then the lightweighting of foam. So this is the taking out of the volume of the foam and using fillers. Graphene in those fillers and other 2D materials can be used to actually substitute the strength losses. And we can demonstrate that from the neat polyurethane foams, we can get significant increases in compressive and tensile strength just by adding those systems. And it's all about that kind of formulation and optimization. Just one example of just how kind of the automotive industry is adopting these machines. So if you take, there was a particular polyurethane foam, and it was mainly, the project was around heat endurance for components. So this was looking at the supply chain, it was looking at how do we get these performance materials into the supply chain that will give them the heat endurance, because it's about reduced maintenance on the components, reducing the stress on the components. So there was a 20% improvement in the mechanical strength, but also there was a 30% improvement on the endurance for heat benefits for this particular foam. But because we were using the supply chain, within 12 months, we actually got those trials into production. And for this particular vehicle, there's over 5 million vehicles in the US. But this is not uncommon. Why have Ford not promoted it? Because around graphene and 2D materials, it's around that commercial benefit sometimes. So the company that's making this foam, who's got an exclusive license with Ford, this is actually giving them kind of an edge. And they're moving this kind of technology now onto those electric vehicles. So bringing kind of graphene into the supply chain, you don't hear about it in terms of publications, because once you then move into the commercial arena, you're starting to bring in you're starting to get an edge over your competitors. But Ford are quite happy for us to share this data. Another area is membranes. So obviously desalination, water management, quite highly appropriate for this region. We do have a casting line at the Geek. So this is about 12 meters long, but it's got various capabilities, and it's a roll-to-roll system. But we start off by taking standard membranes. So we're partnering with Khalifa University, for example. We partner with various universities throughout the world, but it's taking their kind of membranes technologies and getting it into the demonstrator. So they're the leading edge discoverer on their particular membrane system, but we can actually get it into that spiral wound or hollow fiber system. As one example, so this was on a spiral wound system. We've taken a standard membrane. So if you look at the base polymer, we wanted to do various designs of the base polymer. But how do we then take a base polymer with a known rejection rate and then populating it with nanomaterials? How do we improve that rejection rate? So you've got the theoretical from the papers. We then work on a 1 meter squared, replicating their formulation. So we've taken their nanocomposite or their graphene dispersion. We've populated it onto the base membrane. But then how do we then take that base membrane with an uplift into commercial applications? So this particular one, we've actually gone within a 12-month period from a 5 centimeter square membrane, which was tested into the lab, and we're currently on 30 meters long and 300 mil wide, 10 meters squared of membranes, and we're reproducing this on weekly runs. But the process to go from the lab showing consistency in the up performance of the membrane with good flux, and then getting it into large scale, because we need to get it to this scale, because then we can transfer this into a spiral wound system. So the demonstrator is actually a cartridge which is about 300 centimeters wide, but it's about 10 meters of material in this particular system. And it's been used for desalination and aggregate, so it's salt removal, but also one of our spin-out companies has been using it for PFAS removals as well. But we've also got other examples of membranes manufacturers which are not using spiral systems, but they're using hollow fiber systems. Now, that's completely different technology. We're obviously clearly not using the pilot scale for this, but we've actually built spinneret systems for the hollow fiber systems using their MOS2 for PFAS removal systems. But we go through the same process of engineering. The way we address the challenges has always been the same. So we take the lab scale, we work on the volumes, how do we actually produce the larger volumes, whether it's on the nanocomposites on the sheets, on this reduction bath system, coated and reduction bath system, or we've actually derived a spinneret system that allows us to coat and then go to the 300 meters or so spinneret systems that they require then, that they can then get into a cartridge, then that can go through a cross-flow system. So we're using the supply chain to actually generate the standard cartridges, which we can then issue the cartridges to the manufacturers, and then we can actually demonstrate in standard cross-flow systems the performance of either spiral wound or spinneret systems. So companies come to the Geek to actually use these kind of systems to actually de-risk. So they don't, this particular piece of kit which is commercially available, you can actually go to Mathis, because it's a Mathis manufacturer, and actually buy this specification for a given application. So working with the supply chain is another aspect of what the engineering centre does with our partners. We actually start to identify who your equipment suppliers may be as well. So this was focused on membranes. Battery systems, so we take all aspects of the battery systems. So this is taking the nanocomposites, and we've heard some examples today how we take them on for the anode development, the cathode development. We go through the coatings, we go through the calendaring systems, the cuttings. But what we do at the Geek is we manufacture the pouch shells. So it's upscale from, we can do the pouch scales of all different sizes. We've got dry rooms and all the abilities. We do about 300 pouch shells a week. We don't need to go to any higher volume, but what we can do very iteratively is go from a formulation development in a slurry and getting it into testable pouch shells. And these are multi-layer pouch shells as well, not single-layer pouch shells. They're typically 10 layers, and we go through industrial processing, industrial volumetric sampling, and we can also test in demanding environments as well. So we can actually do these electrical performance tests, we can do the volumetric testing, we can also then do destructive or non-destructive tests as well. So if you're looking at dendritic growth, for example. So at the university, it's all about that support network, fundamental research. How do we take a nano development and how do we get that through into a cell that industry is prepared to use and can recognize the data. So the cells that we produce, we can get into the pack, and then the pack can be tested by the industry. So it's that rapid acceleration of testing, which is quite important. So these are just some examples of areas. I mean, energy storage systems, you know, it cuts across so many different aspects. You know, we're talking about lithium-based systems, we're talking about sodium-based systems, supercapacitors, but the principle is the same. We're looking at the engineering challenges about how we adopt all these different types of technicians. So we don't focus on one particular aspect. We look at the challenges that dendritic growth occurs. We look at, so each technologist may have their own way of solving dendritic growth, but how do we get that into standard systems and how do we test it? So it's about the upscale challenges. So the companies that come to us, they own the IP. So the projects that were all delivered are owned by the IP, they're owned by the inventors, but we help them on that scale-up challenge. So we work with roadmaps. This is just one typical roadmap about the lithium tracks. You know, you might address some developments in different binders, for example, on LFP system, LTO systems. So the energy group are actually working on the challenges around upscale. So we're not focused on, we're not going to do our own research, it's not that. We take the research from our partners and we work with the supply chain and we look at different generation batteries, about how we do different adoption of different nanomaterials, for example. Because as you know, in any given battery, you know, all these competing challenges. Sometimes you might adapt some one graphene in one. So we talked about ZTC systems the other day, which is quite interesting. But how will that work with the given electrolyte? All these one effect can affect the other. And we look at those iterative cycles, and what we aim to do within the Geek is actually get those iterative cycles down to as quickly as possible to accelerate the adoption of technologies. So we've been looking at galvanometric systems using silicon batteries. Again, it's all about the next generation batteries, but it's all about that rapid adoption. Other areas is depositions. So this is just in our printing systems. These are biomedical sensors where we're printing hundreds of sensors per, using conductive inks. So again, this is just another rapid prototyping technique. We've got data, just say we call it State of the Union, but then this is just about printed technologies. So yes, we've heard about the National Graphene Institute and the ability to make devices and wafers, but this is about low-cost electronics for different applications, thermal management, and we've done comparisons between different types of printing systems. Some additional data here, some anti-corrosion. So anti-corrosion is another example. So this is rebar, but how do we use ASTM standards for different types of corrosion systems? One aspect I wanted to bring was we're getting standard GMP systems into anti-corrosion, but sometimes it's the blend of the graphenes as well. Material selectivity is fairly critical in some of these applications. So this was 1,000 hours in a corrosion move, and the GMP version 3+5 actually gave virtually full coverage in terms of an anti-corrosion. So there's plenty of data. So these are intrasemestic coatings for fire retardancy. Again, these data here that you can actually reduce the burn time or the time to, what they call the time to failure. So it's the industry who make fire retardant coatings have obviously read literature, but then they want to start to do trials about how they adopt graphene 2D materials into a particular system. So these are the types of kind of mindsets that we go through. So these are abrasion resistance and wear resistances, and then all this is supported by the engineering side. So we work with the supply chain, the equipment supply chain, the ability to be, how do we actually get the engineering design into production? Because there's various aspects. So if we take this engineering design here, the cost of the design of the fabrication facility for that was around $10 million. That was a large capex for any startup with unproven technology. So we actually managed to produce much lower cost. They didn't need the facilities. We built it in the pilot hall, and we do this as a part of the normal cycle of the development. So we call it the engineering services, where we've got access to process control engineers. They actually bring in things like the ladder logic, they bring in the safety controls, so the design consultants then can take a very basic system such as this, and then how do you de-risk that and that with the manufacturers going forward. So there's many, many aspects of engineering, so it is just as important as the actual process itself. So we whisked through kind of lots of different types of applications as an example, but it's a journey that can vary significantly in time. So we can take some projects that can, getting to the first prototype could be 6 months, but sometimes the first prototype is taking up to 2 years. It really comes down to the individual, where the emerging technology is at, or where potentially the multinational is at in terms of adopting their kind of technology going forward. So happy to take any questions now, Omar, if that's...
Thank you, Professor John, for the nice presentation. I really enjoyed your slides. My name is Mujib, Khalifa University, where we've been having a burgeon, spike in applications of graphene for various research stuff recently. I want to ask a question, or it's like a two-in-one question regarding your insights on the advances with the sustainability in graphene production.
Yes.
So in the sense that, are there any interesting progress you can share with us with respect to sustainability issues related to the production as compared to Homer's method, for instance, and the impacts on the life cycle assessment? And then quite relatedly, some people have reported that graphene can be produced from stuff like waste carbon or agricultural product, but some others have criticized that the graphene has a bit of a low quality. So I wanted to take your insights regarding these issues. Thank you.
It's a very good question, and you are right. I mean, if you look at currently, the large volumes of graphene are derived from graphite, and they go through the electrical chemical exfoliation. So in terms of a sustainability program, it's not best to mine and to chemically process. But you are right. If we take one company, for example, called Whittaker, they have what they call a plasma loop reactor, where they're taking flue gases from petrochemical processes or landfill, which is largely methane, and their plasma process can actually extract hydrogen, usable hydrogen, and recrystalline the graphene, which is usable. So currently, Levidian have got 3 loop reactors throughout the world undergoing industrial trials. So we're actually getting usable graphene or usable graphites from these feedstocks. So the answer is yes, there's lots of research where graphene has been derived from coconut shells, from orange peels. There's a whole raft, but it's about scale. The petrochemical companies are seriously involved in using their feedstocks. So from high rich coke from some of their chemical processes are undergoing trials now to produce usable graphenes. So we do envisage this within the next 2 to 3 years. It will be a significant step change that most graphene will actually be derived from reusable sources rather than mined out of the ground. But that's a development in the last 3 years. The Levidian program has been quite significant because Levidian are actually a partner of the Geek, so we have seen firsthand the quality of the graphene from those sustainable sources, and they're actually very good quality. They've got quite large surface areas and comparable to the mine graphites at the moment. So yes, I mean it is going to be a disruptor, and I think Levidian this week are actually auctioning 15 tons of graphene for use by an application. So they're already at the volume. And there are also, certainly in North America now, there is a significant uptake in graphene production from reusable sources. So yeah, it's a very good question, and we do see within the next 2 to 3 years that certainly most of the usable graphites will come from renewable sources.
Okay. Yeah, so it's a very nice talk. I have just one curiosity. You said quality graphene. So when you say quality graphene, then how you assess this? It's a kind of monolayer graphenes, or it's a multi-layer graphene, or it's a reduced graphene? I mean, what kind of graphene you are saying quality graphene for these kind of applications that you talked about?
Yes, so the market has got, so what is usable graphene? So if you look at the metrology agencies such as ISO and in the UK, we work with the National Physical Laboratory that have defined graphene as between 1 and 7 layers, and has a particular defect peak under Raman analysis. So we have actually quite a good measure in terms of what is graphene, and so the graphene suppliers we actually use at the Geek do quantify their graphene in terms of defect peaks and their numbers of layers. There's a lot of suppliers which will actually define the actual aspect ratios of their graphenes. Not all graphenes are best used in different applications, so as we know there are families of graphenes which can be used in many different applications. So there's still a lot of knowledge exchange to occur about the right graphene for the right application. So one particular nanoplatelet or area graphene might be good for energy applications, but not necessarily good for construction materials, for example. If you then take the other manufactured graphenes, like the grown graphenes, like from CVD, for example, where we can actually grow monolayer graphene over a relatively large area, but then you've got transfer problems of the graphenes as well. So we do understand in the community, the responsible users in the community, where those graphenes are and how to quantify them. But there are still significant disruptors out there of people claiming that they're graphite, they're calling it graphene-like material, and when you try to use those graphene-like materials and using it in the same formulations, they're not actually getting the performance uplift that they were expecting. So there is still a long way to go to actually, but it's getting better. You know, compared to 5 years ago, there's much more data available now, and industry is a lot more savvy now as to, and they have, along with the R&D communities that they've started to employ people who've been studying 2D materials who can actually quantify it much more accurately. The adoption of graphene has certainly started to accelerate, but we're also seeing that with other 2D materials as well. So yes, it was a challenge, say 5+ years ago, but it's certainly getting better.
All right, to stay on time, please find John in the break and ask whatever questions. Let's thank John again.